Are we live? Are we live? We're live. Hi all, welcome to another developer live stream. Thanks for joining us again this month. More TensorRT-LLM learnings. We're joined by two new friends on the TRT-LLM team. This week we're talking about, or this episode we're talking about implementation and optimization for multi-token prediction for DeepSeek R1 in TensorRT-LLM. My name is Zach. I'm part of the NVIDIA developer community team. We have Joe helping us behind the scenes as always. And this time we're joined by Yue and Fanrong, who are here to talk about TRT. Fanrong is a senior architect for TRT-LLM and Yue is a developer engineer. Again, thank you for joining us for this developer live stream. This time is for you. So because questions are a thing, please ask often when you can. When you can, we'll pause in between a few slides to take some questions and answer them throughout the stream. And also we'll take some time at the end of the stream, maybe about 10 minutes to answer any questions that you may have. So I'll let Fanrong start. Go ahead.
Hello everyone. Thank you for joining us today. I'm Fanrong from TensorRT-LLM team, and together with Yue, we will be talking about DeepSeek and MTP, which help DeepSeek model achieve better performance, especially for the mean latency scenarios. I mean, with the batch size one. Yeah. So here's today's agenda for the talk, and we will start by talking about what does MTP do to help boost the DeepSeek performance, and how we implement the MTP in TensorRT-LLM, and then about the MTP optimization for better performance, and finally we will show the results and our future works. Yeah. Okay. Let's start with the first session. The DeepSeek MTP method is inspired by a previous academic paper. And DeepSeek originally used this method to help model training. As we can see in the figure, if for the normal training, we will only input all the input tokens to the model, and then we will get the output and compare with the target token. We can get the cross entropy loss, and then we use the loss to update our model. And in this way, we can only predict one token here. For example, in this example, we input token from token 1 to token 4, and then we can predict the token 5. Yeah. But with MTP, MTP will add 2 additional layer or 2 additional MTP modules to the model here, and we can see from the figure, MTP module 1, MTP module 2 here. Yeah, MTP module 1 is used to predict another new token. We can predict token 6 here, and the next MTP module we can predict the next token 7 here. Yeah, so in this way, MTP can extend the prediction scope to multiple tokens rather than only one. Yeah, and so it can help train the model better, and we can achieve better model accuracy. But MTP, this MTP method can also be used for speculative decoding to improve the generation latency. Because all of those MTP modules are trained along with the main model, so if we use those MTP modules for speculative decoding, we can get a better acceptance rate. So before introducing MTP inference, let's take a brief look at the speculative decoding. Okay, speculative decoding technologies usually divide the process into low-cost draft stage and parallelized verification stage. In the draft stage, we will use a small model or a subset of layers in the main model to predict the draft tokens. As you can see in the figure, we will get previous without the speculative decoding. We only input in the generative phase. We only input the golden token G here. We call it golden token. It is an input token. Yeah. And with when we using speculative decoding in the draft stage, we will predict the draft tokens. In this example, we will predict A, B, C, D, E. They are the draft tokens, and we will input all of those tokens, including the golden token T and the draft token A, B, C, D to the main model, and then we can get the output. We can get the logics after sampling. We can get the expected output tokens. Yeah. For this forward, I mean the main model forward, it is the verification stage. We will in the verification stage we will input all those tokens to the model and predict the expected tokens, and then compare the expected token with those draft tokens. Here we will compare A, B, C, D, E, and the output token A, B, C, H, K, and J. And if they are matched, so we can accept those tokens. And so in this way, we can predict multiple tokens in only one iteration, not one token. Here we can in this iteration we can accept A, B, C, H. A total of 4 tokens accepted. So in this way, speculative decoding can bring some performance speed up. Yeah, this is the speculative decoding. So any question about this part? No.
We have one question. Let me bring it up.
Okay.
Asking Fanrong if you'd be touching on how to improve the causal chain to optimizing token usage for LLM.
Causal chain to optimize token. I think for this talk, I mainly talk about the MTP and the speculative decoding. And for more details, we will discuss it in the later slide. Yeah. So I think how to optimize. I think we can talk about it later. Yeah. Okay.
Yep. Let's move on.
Go forward. Okay. Let's talk about the MTP inference. When we use MTP to accelerate the inference, there are 2 different MTP methods. The one is we call it MTP vanilla and MTP equal. MTP vanilla is it use different MTP module to predict different draft tokens. Each MTP module predict 1 draft token. Yeah, in this way. It can support the checkpoints that with different MTP modules in the checkpoints. For example, we may have some model with MTP modules. They those MTP modules have different weights. So for such checkpoint, we will use MTP vanilla to support it. And MTP equal, it is different. MTP equal use the same MTP module to and repeat multiple times to predict multiple draft tokens. For each draft model forward, we will predict 1 draft token, and for the next forward, we will predict the next draft token. But we will only use the same MTP modules. Yeah. The difference of MTP vanilla and the DeepSeek MTP vanilla and MTP equal another difference. It's about the KV cache. MTP vanilla will use different MTP module, and all of those modules have their own KV cache. But MTP Eagle will share the same. So this is another difference. For the DeepSeek V3 model and DeepSeek R1 model, in their official checkpoint, there is only one MTP module layer, so we can use it. The default path is MTP Eagle, but we can also duplicate those MTP modules to use MTP vanilla to support this feature. Yeah, this is the overview of MTP. So let's take a look at the details about MTP vanilla. In the context phase, we will input this is the main model. We will input our prompt to the main model, and we will predict a new output token here. Here we call it T5 token 5, and then for the MTP module forward, there will be a shift on the token. For example, in this example, the prompt is a token. The prompt tokens are from token 1 to token 4, and we will predict the token 5. And for the MTP module forward, here I mean the MTP module 1, we will shift the token, and we will input the token 2 to token 5 to the MTP modules, and also their corresponding the hidden state. Yeah, here we will input all the hidden state to this MTP module, and then we will use this MTP module to predict the first draft token. And for the next MTP module, we will for the token there will be another shift, and also we will also shift the hidden state. And in this way we can predict another new draft tokens here. Yeah. After the context phase, we can get the golden token token 5 here, and some draft token from draft token 6 and draft token 7, and some other legal draft tokens. In this way we can we finished the draft stage. Yeah. And for the generative phase, in the generative phase, we will input the golden token T5 here, and all of the draft token, and to input all of those tokens to the main model, we will get the output token and their corresponding hidden state. And then we will compare the output token with the draft token. We need to do the verification. Yeah, we need to check which draft tokens can be accepted, and which draft token we need to drop. Yeah. So after the verification, we will input the accepted tokens to the draft model here, and here for MTP vanilla, and for the draft modules, we need to input a total of k different tokens, and in this way we can predict the and zero corresponding hidden state here. Yeah. In this way we can predict the new draft token for the next iteration, and then there will be a similar shift to the token and the hidden state, and input after the shift we will input those token and hidden state to the next MTP module predict the next draft token. Okay, this is the generation phase. So in this way we can predict draft token, and we can do the verification. So any question about MTP vanilla?
There are two questions. One question is, actually, let me bring it up. What's the benefits and cost of using MTP Eagle here instead of MTP vanilla? You may have answered this.
Okay, let's back to this slide. MTP Eagle can MTP Eagle, we don't need to duplicate the MTP modules, and it can save the TPU memory consumption, and we only use one TP module. And another benefit is we will talk about it later. And in these two slides, we only talk about vanilla. In the next slide, we will talk about the Eagle. So there are some differences. We can talk about it later. Yeah.
All right, we can move on.
Okay, so the MTP Go here. MTP Go is different with MTP vanilla. The difference mainly in the black box. Yeah, here I highlighted the black box. In the context phase, the first MTP module forward, it is the same, but for the subsequent MTP module forward, they're different. And for example, here, MTP vanilla will use MTP module 2 to predict the new draft token, but MTP Eagle will use the same. All of them use the MTP module 1 here. Yeah. The other difference is about the input token and the input header state. For the first MTP module forward, we can it is the same as the MTP vanilla, but for here in this example, for the second MTP module forward, we only need to input the draft token predicted in the last MTP module forward. Yeah. Here we will only input the draft token 6 here to the MTP module, and also the corresponding header state. So it will be much easier. In MTP vanilla, we will still need to input many different tokens and many different header states. Here we only need to input one token here. So this is another benefit compared with MTP vanilla. Yeah. And about the generative phase, difference also in the red box. In the generative phase, for the first MTP mode forward, we will input all of the accepted tokens. In MTP vanilla, here we need to input a total of k different tokens. But here we will input all of the accepted tokens. And for example, if there are only one token is accepted, here we will only input one. But if there are a total of 5 tokens accepted, so here we need to input 5 tokens, and also we need to input their corresponding header state to the MTP modules. Yeah. For the second MTP forward, it is similar with the context phase. We only need to input the draft tokens predicted in the last forward. Yeah, here this is the new draft tokens, and we will input it to the same MTP module, and we can predict the next draft token. This is the difference between MTP Eagle and MTP vanilla. Okay. So that's MTP inference and about MTP vanilla and MTP Eagle, and then we will talk about how we implement MTP in TensorRT-LLM. Yeah. Okay. In TensorRT-LLM, we can support those 2 different paths for both MTP Eagle and MTP vanilla. MTP Eagle is the default path for DeepSeek V3 and DeepSeek R1. And this method is used when there is only one MTP modules in the provided checkpoint. For example, in the official DeepSeek V3 and the DeepSeek R1 model, and there is only one MTP layers in their checkpoint. So this is the default path for those 2 models. And MTP vanilla is used to multiple different used to the model that with the different MTP modules in the checkpoint. For example, maybe someone need to train off and train their own models with MTP, and this model may have some different MTP layers. So different MTP layer have they don't share the same list. So in this way, we need to use MTP vanilla. Yeah. About the overall workflow, we put in the context phase, we will input the prompt to the main model forward, and we can get the next token and the corresponding hidden state, and then input those tokens to the MTP modules forward. We can predict the draft tokens. So we will put all of those forward into the model engine forward. So all of them are in the model engine forward. And in the generation phase, we will in the generation phase, we will get the new tokens and the draft tokens. We will input all of those tokens to the model main model forward, and then we can predict the next tokens and their hidden states. And the next step, we need to verify which draft tokens can be accepted. And here in this step, in this verification step, we need to compare the predicted new tokens and the input draft tokens, and to see which tokens can be accepted. Yeah. After that, we will get the accepted tokens, and we will input those tokens to the MTP model forward to predict the next the draft token for the next iteration. Finally, there will be a revealing key cache. What does it do? In the verification, not all the tokens are accepted. There are some draft tokens. We need to. There are some draft tokens are rejected. So we need to remove their key and values from the key cache. So here we need a revealing key cache step. Yeah. And all of those ML model forward and verification step and the MTP model forward, all of those are put into the same model engine forward. In this way, we can enable MTP and with other different TensorRT-LLM features, for example, CUDA graph and OLAP scheduler. CUDA graph, with CUDA graph, we can boost the model performance. Especially for the model with for the case with a small batch size, CUDA graph can help a lot. And OLAP scheduler is another important feature to hide the CPU overhead. So so our current MTP workflow can enable those two features, and it can also help achieve better speed up. Yeah. Oh, I forgot another important is that here both MTP Eagle and MTP Vanilla share the same workflow in TensorRT-LLM. The only difference of those two MTP paths are in the MTP module forward. They have different MTP module design. And about their MTP module design, let's take a look about the Vanilla and the Eagle. About MTP Vanilla, in the generative phase, we need to input a total of k different tokens to the MTP modules. But there will be such a case that the accepted tokens, the number of accepted tokens is less than k. So we can't find k different valid tokens as an input. So here we need to save the past tokens and the hidden state. In this way, we can concat those old tokens and those old hidden state to the current input, and then we can get a total of k different token and hidden state to input as an input of the MTP modules. Yeah. So from the implementation part, it is not easy. Yeah, we need to adding two new tensors for each request and to save those tokens at the stage. Yeah. So here in the figure, after the main model forward, we will sample and accept, and to get the accepted tokens, then we need to update those two, update the pass token and pass hidden state, and then use the pass token and pass hidden state to prepare the draft inputs, and then to predict different draft tokens. Yeah. And in the right figure, is the MTP module design. Here we can there will be two S norm, and then compare the features, and then a linear, and then there will be a transformer block. This transformer block is the same as the transformer blocks in the DeepSeek main model. So they also have the MOE layers in this transform block. And we will get the hidden state and the bodies, and then after sampling we can get the tokens. This is the MTP vanilla, but MTP Eagle will be much more easier. We can only we don't need to see those past hidden state and past tokens. So the only thing we need to do is we need to prepare draft input for the first MTP forward, and for the subsequent forward, it will be easier. We only need to input the predicted draft token to the MTP module, and then predict the next draft tokens. Yeah, it will be much easier here. So we won't talk more about this. Yeah. To support MTP, especially for the verification stage, I mean for the main model forward, I mean we need to make some change to the attention. For the normal generation, mainly about generation phase. For the normal generation attention, we only need to input one tokens, but here we need to append the draft tokens at the end of the input token. So there are a total of many different input tokens in the generation phase. So here we need to extend change the attention kernel to support such a pattern. And the main change is about we need to use a different attention mask here. And so here is the generation kernel attention kernel mask, and for MTP vanilla and MTP Eagle, they are a little different. This is what we need to change in the attention part. Yeah. Okay, that's about the MTP implementation in TensorRT. Any question about it?
If I'm wrong, we have a couple of questions. I think you answered them in the chat, but maybe you can, answer them aloud. One of them is, could you please, there we go. Can you explain why we need to use the same MTP module?
Why we need to use the same MTP module? Yeah, a good question. Here we only the MTP Eagle use the same. So use the same MTP module and MTP with. But for MTP vanilla, we can support use different. Yeah. So about why this is why we use only one. Another reason is about in the official DeepSeek released model. I mean the DeepSeek V3 and DeepSeek R1, and there is only one MTP there in their checkpoint. So here we want to support it. Yeah. If you have a checkpoint that with multiple different MTP layers, you can use MTP vanilla to support it. Yeah.
Great.
Hope this can answer your question.
All right. Thanks a lot, Panro.
Okay. Now I'd like to hand it over to Yue. He will introduce the optimization and our results and our future work. Pass it on to you.
Thank you, Fan Rong and Jack. Hi guys, welcome to our live, and I'm Yue Weng from TRT-LLM team. Next, please allow me to introduce MTP optimization, relaxed acceptance. Let's talk about the background and the motivation first. We know that the models with reasoning ability, such as DeepSeek R1, will first break down and analyze the problem at the beginning, just like we humans think about the problems. The model will gradually get some answers and finally output the response that the user wants. We can take this as an example. We want the model to translate two sentences from English to German. We can see that there are two phrases, the thinking phrase and the actual output. During the thinking phrase, these two sentences will be translated separately, including some grammatical requirements, and this will also be published and modified. And finally, the output is made. From this example, we can see that the thinking phrase may occupy a lot of output tokens. We intuitively believe that these output tokens are auxiliary to the final output, and the quality of this part may have limited impact of the final output result. So can we speed up the thinking phrase by treating the quality or the accuracy? This is exactly the motivation for us to propose a relaxed acceptance, a relaxed way to receive the job tokens. Currently, we accept the job token in a straight way. After the job token pass through the main model, we will sample the logic with the top one strategy, and we get the expected tokens. Only when the expected tokens are straightly the same as the job token, we can accept this job token. But now we have relaxed acceptance, which is a more aggressive method and only occurs in the thinking phrase. When a job token appears in a candidate that generated by the main model, we consider that this job token is reasonable and can be accepted. Now we have two knobs for the relaxed acceptance. The first one is the top M, which determines how many tokens we sample from the logic, and this logic was generated by the main model. The reason for this knob is that the semantic of the top M tokens are usually close, and they may be all suitable for as the next token. The other knob is the probability threshold, delta. Based on the top M tokens, we further screen, and only when the probability of this token is no less than the top one probability minus delta, and can it be retained in the candidate. This purpose is to filter out the token with a large probability gap between the top one tokens, which may be totally different from the top one. It should be in phrase that we only do the relaxed acceptance during the thinking phase. Once the thinking phase is over, we will return to we will fall back to the straight acceptance. Okay, let me hold a second here, see if there are any problems. Okay, let me move forward. Next, we will introduce our evaluation. In this figure, we show the result of DeepSeek R1 671 billion with FP4 mixed precision. For the mean latency scenario, we test on 8 B200 GPUs. The parallel practice are TPA and EP2. The batch size is always 1. MTP Eagle is used. We test 10 requests with 1K input and 2K output. The horizontal axis is the number of different MTP, and the left vertical axis is the acceptance rate. And the right axis is the acceptance rate, and the left is the TPS. Different colors curves represent different configuration, such as CUDA graph and overlap scheduler, and also its relative acceptance rate. As we can see, when MTP3, we achieve the best TPS, and compare not using MTP, we can get a speed up of 2.16 times. Although more MTPs more MTPs can improve the acceptance rate, but we also need to consider the overhead, which will increase the time to generate and verify the job token. There is a trade-off here. The improvement of the CUDA graph and TRT-LLM MOE is significant, with average speed up over 7 times. This is a key setting. The overlap scheduler also brings a 3% performance improvement. That is our accuracy study of the relaxed acceptance. We still use MTP Eagle and FP4 checkpoint. The metric here is the typical data set of artificial analyzed benchmark. We can see that the relaxed acceptance has limited impact on the output quality. This feature is worth to try. The last part is the future work. Our future work is mainly divided into two parts. The first part is to use a tree-based job token generation method to explain the candidate combination. There are two forms of tree. The first one is the full tree, and which each node will expand the fixed subnodes. The other one is the dynamic tree, which will dynamically construct the tree based on the probability. But the mass of this tree are quite different. They are not causal mask anymore, and this requires some MLA kernel adaptation to spot this special mask. Another future work is Eagle 3 spot, and Eagle 3 can leverage different levels of feature and to generate a more high quality job token, which can also be helpful to improve the acceptance rate. Finally, we leave some useful links here, including the relative technical blogs and documents. We only call for contributions and any useful issues. Please help us to be better. Yes, the bar is what we shared. Thank you for your attention.
Great, thanks a lot, guys. There's a couple of questions that came in. I'm going to put them up, so have a look. What would be the process of verification and acceptance process before accepting the token to the MTP module?
Oh, I think we can see these slides. Yes, maybe we can refer this slide. Before we accept the job token, we will let this job token to go through the main model, and then we will get some logic here, is it right? And then we will use this logic to sample the expected tokens, like we get A, B, E, F, H here. But our job token generated by the previous iteration is A, B, C, D. So we compare one by one with the longest prefix match. So we can only use accept A and B, but when we try to accept the second one, it was not matched, it's mismatched. So we can only A, B, and E. Why we also accept E? Because B is accepted, so it's not so the E is the golden token, and which can also be accepted. And hope my explained can meet your requirement.
And one more question. What would be an improvement to generate draft tokens in an MTP model?
To generate draft token in MTP. I hope I can understand your question clearly. And in my understanding, I think you might ask about compare with the MTP vanilla. I think the improvement of MTP module will generate more high priority job token. Because we get this conclusion from the acceptance rate. The MTP Ego may have slightly better acceptance rate compared to the vanilla MTP vanilla, but most of the time they are close. And MTP model will be improvement to generate job token in MTP module. And yes, that's my question. That's my answer. Sorry.
Great. And I think we have one more questions keep rolling in. We still have about 10 or so minutes left. This one is, what are the hardware requirements using Eagle mode for this example? And how much more memory is required compared to vanilla mode?
The first thing I thought is it will require more GPU memory to store these one more layers weights, because MTP Eagle will only have one weight, and we will reuse this weight for multiple times. So we need extra GPU memory to store this weights. And to vanilla mode will have the different module will have different weights, so it will need more GPU memory compared with the MTP Eagle. And I think that's the most hardware requirements that we need to consider. And maybe it will reduce some memory for the KV cache, because we will need more GPU memory to save this weight.
Thanks for the question. Another question is, is MTP equals 3 suitable for low batch real-time inference on Jetson class edge devices?
Sorry, I don't have much experience here, but I think it's worth to try. Because it depends on the computing ability, and actually in the Jetson class edge device, it will not have a very high computer capability. But when the batch size is very slow, like we only use batch size once, we still have some redundant computing results. So like the MTP or other speculative algorithm is actually use more compute result to save the time. So I think it's worth to try with MTP3 or MTP1 to see whether it can bring some improvement. Yes,
All right.
it use more sorry. It use more GPU computer results to save the time to reduce the total iteration. One iteration will generate maybe more than one tokens, so it can save the time. But it also depends on the weight of the models and the batch size. That's all. Sorry, Zach.
Oh, great. Thank you. I think that is the last question. We want to say thank you for joining us again for another live stream. Join us for the next one. Stay tuned. This particular stream is going to be recorded and will be available through the same link on YouTube, on our NVIDIA Developer YouTube in the live tab. So please come back and watch this if and when you can, just to catch up. And follow up on our Discord and forums. Links have been provided throughout the chat. So please connect with the team, and we look forward to seeing you next time. And thanks, Yue, thanks, Fanrong, for joining us.
Thank you, Huanrong. Thank you, Dex. Thank you, guys.
All right, thank you guys.
Bye bye.